When I was a kid in 1960, pizza cost 15 cents. The subway fare was 15 cents. By 73, the subway fare had gone up to 35 cents. Pizza was roughly 70 to 35 cents. So 86, but what does pizza cost nowadays? 2019. Not $5 a slice. You don't eat much pizza. Where do you eat pizza? $5 a slice. That would mean like an 8-slice pie. An 8-slice pie would cost like $40. No, I don't think so. Right? No, it's more than $2. Maybe $2.50. Maybe $2.50 a slice. Okay, $2.75. Okay, let's say it's $2.75. How much is I'll call it $2.50. How much is a subway fare? Bingo. What do we have here? Whenever the subway fare goes up, the pizza price goes up, right? So now that's what we call, there's an association there between the pizza price and the price of the subway fare, right? Now, technically, we call that a correlation. There's a correlation between the price of pizza and the cost of a subway fare, right? The undiscounted. I mean, you can get a multi-fare ticket and stuff like that. You pay a little less, or you can buy a whole pizza and you cut it up in slices, you pay a little less. But it seems like it tracks very closely. Not always exactly the same, $2.50, $2.75, $1.25, $1.35, not always exactly the same, but it seems to follow a pattern there, doesn't it? That kind of pattern, that kind of association, when it involves numerical data. This is numerical data, right? The price of pizza is a number, and the subway price is a number. It's numerical data. When we see an association between numerical data, two sets of numerical data, in this case, two variables, pizza and subway, right? Then we call that a correlation. There's a correlation between the cost of a slice of pizza and the single fare for a subway ride. Okay. That doesn't always correlation. When I say the word correlation, it doesn't mean that one causes the other, right? So for instance, I don't think the MTA meets in secret on weekends and says, hey, I just bought a slice of pizza, it cost me $3.25. We got to raise the fare, right? So I don't think that happens. It's possible, but I don't think so, right? So this happens to be a spurious correlation. There is an association here. It's real. As one goes up, the other one goes up. And we can actually plot this and look at this and see what this association looks like. Let me see if I can do it easily from Excel without having to go crazy here.
What about subway access and rent?
On rent, yeah, that might. Well, I guess anything that has goes up with price increase with inflation probably would apply. I don't know that it would be as close an association as this, but let's see if I can't insert. I think it is. Okay, let me just draw a little graph here. I'm going to draw a graph called a scatter plot. And what this represents is on the bottom is the slide in, I didn't cover the word pizza and subway, so I didn't mark the axes. I really should have. But on the bottom here, let's see, 250. On the bottom is the price of a slice of pizza, and on the y-axis, the vertical axis, is the cost of a subway token, right? Cost of subway fare. So if you look at that, you can see as one goes up, the other goes up. And this scatter plot, the way this works is that dot represents the X and Y coordinates that represent the cost of pizza, the X-axis, which is cost of pizza, and the Y-axis, which is cost of subway. So this dot is a 250 on the X-axis, pizza, and a 275 on the Y-axis for the subway fare. And if you look at this, you can imagine drawing a line up here. Now, not every point, if I drew a straight line up here, not every point would fall on that line, right? Some points would be on that line, some points would be out that line, but all of these points are remarkably close to that line. That suggests that there's a strong association, a high correlation, a large correlation between pizza price and the price of the subway. So, but we know they're not direct. One is not causing the other. Okay. Now we can have a lot of associations like that. Like for instance, what if I told you? Does this sound believable to you? That the number of firemen that respond to a fire is associated with the amount of damage in the fire. Make sense? In other words, if a lot of firemen respond, there's a lot of damage. Why? Not because the firemen are doing the damage, because when there's a big fire, a lot of it, right? So there we can see underlying association. We can see it's not really the fireman causing the damage, but we can understand what's causing the correlation. This one with the pizza and the subway probably has something to do with inflation more than anything else. But the one with the firemen has, we can see that there's an association. More firemen, more damage, right? We can see there's, again, that's numerical, number of firemen versus the cost of the damage in a fire. And so that, yeah, in fact, just so you know, just for entertainment value, there is this guy called Tyler Vegan, and he has a website, spurious associations, yeah. And he's found all of these different correlations. So the more people eat cheese, whoops. I don't know what that is, but I have to accept it, I guess, Oh no, God, never allow. Okay. More, now there's some other ad here now. Boy, it's almost not worth using the internet anymore, Really, I mean, it's getting ridiculous. It's really frustrating. The more people eat cheese, the more people are killed by their bed sheets. Now he has a website. He has a website. Literally has a website. Let me go back here and see if I can find the link. He has a website where he maintains many of these. Suicide by hanging, strangulation, and suffocation are associated with U.S. spending on space science and technology. Number of people who drown by falling into the pool correlates with the film's Nicolas Cage. And look how close the association is there. Yeah, well, it's true. I mean, it's not making these numbers up. Per capita cheese composite, we just saw that one. Divorce rate in Maine correlates with the per capita consumption of margarine, right? Now we know they're spurious. There's really nothing associated, but it just happens by chance that they're associated, but it's a real correlation. The fact that they seem to track each other is real. In fact, on some of these, maybe I have to click into it. I think if I click into it,
margarine and divorce might not be so far off.
yeah. I won't even go there. I have no idea. I don't. Okay. So now, if you look, I'm frustrated here because I'm not seeing the view that I want. Maybe I got to do this. No, I don't want to download it. Spurious correlations. Vegan. Let me reload the page. Maybe that's. Nope, that's not what I want. I'm trying to get up. Here we go. Up here. If you look at the top here, it shows the correlation. There's an R value says R is equal to, like that one's R is 0.66. This one R is 0.94. We're about to learn what that number means. That number is a statistic. What's that? Yeah, that number is a statistic that tells us how strong the association is. That's the Pearson's correlation coefficient. When we're talking about the population of all sociology doctorates and all space launches, we use rho, the Greek letter rho. When we're talking about a sample, when we're looking at two samples, sample of one variable, one sample of another variable, numerical variables. When we're looking at those samples together, instead of the population, that Pearson's correlation, instead of being rho, we call it R, just like we use mu for the mean and X bar when it's a sample mean instead. So R is when we're talking about a sample. Rho is when we're talking about an entire population. Okay, so let me get away from this. So how do we determine what that looks like? How that's going to track? How we're going to analyze that? So I'm going to open up some data here. Actually, I'll tell you what. I think I can open up. No, I'll get a different bit of data. Okay, this is not real data. I'm going to open it up in Excel first. This is not real data. This is just made up data. But let's say that we want to examine if there's an association between a person's age and their blood sugar. That doesn't seem that outrageous, right? As you get older, your insulin sensitivity goes down, and you wind up your blood sugar, your fasting blood sugar might be a little higher, and so on and so forth. I think, what do they use kind of like as a crossover point for diagnosing diabetes? 100 or something like that. So this is fasting blood sugar. This is age. So this is individual. We have not 10 people that's in our sample, and this person's 36. His blood sugar is 65. Fasting blood sugar 65. This person is 52. His is 103. This person's 44. He's 110, a little higher than other guys. Not a straight correlation, but maybe I want to quantify how strong this correlation is. So I can do that. I can do that a couple of ways. I'm going to get away from SPSS for now, Excel, and I'm going to use SPSS instead. Let me just move this to my desktop. Okay, let me make sure things are going okay online. Okay, you guys online can hear me and see my screen, correct? Okay, thank you. Thank you, guys. Thanks. Okay, good. If you have any questions, type in there, and I'll pause and I'll take a look at that.
So
Okay.
rho is letter R?
Rho is like kind of the Greek equivalent of R, right? You would use rho when you're saying the correlation of two populations, two numeric values for two populations, and R when you're talking about two samples. So right now we're going to examine what's the value of R? How close are these two values together? Values of age and blood sugar. So I'm going to open up SPSS. And I noticed a lot of you guys are still dragging your feet on SPSS. And it hurts some people on the exam because they didn't have available, they had to come into school, it killed time for them and stuff like that. So it's really worth having it and working with it yourself and learning how to use it, because it's a professional skill, really, at least for us. Open data. I'm going to open the data I just saved to my desktop. Here it is, age versus blood sugar. This is the same data that's in that Excel file. Open it up. Okay, and here it is right here. So I want to look to see if there is an association between a person's age and their blood sugar. I have two variables. What kind of variables are they? Are they nominal variables? They're scalar variables, right? They're numerical variables, both of them, right? That's when we work with. What's that?
After he points to it.
After I point to it. Well, I was going to wait for you guys. We'll never get out of here. We'll never get out of this place if I wait for you guys. And the guys online, forget it. We'll be old. We'll be old and gray by the time they help me out. Okay, so they're laughing at me because I was pointing at it as I was asking the question. So they're both numerical variables, right? Now think about that now. Up until now, we have dealt with, hang on a second here. We have dealt with, let me get some of the type on here. Okay. Okay, let me increase the size a little bit so we can actually see something. So up until now, we have dealt with situations where we dealt with a nominal and a scalar or numerical data. Okay, so for instance, the nominal data. Let's say that nominal data had two possible values. What would that be? That would be like male and female, diabetic, not diabetic, left-handed, right-handed. That has a U in there, right? That's two values, that nominal variable. And the numerical data is scalar. It's just some number, right? It's a number that represents something. In this case, in one case might be male and female, and it might be BMI, or it might be height, or it might be weight or something like that. And we can compare male heights to female heights. And what did we use to test the hypothesis that whether or not these two groups have the same mean height or BMI or whatever? We use a t-test, right? We did hypothesis testing and we did a t-test, right? And when we had three or more values for the nominal variable, and we were looking at it from the point of view of a scalar variable, right? What test did we use then? Compare several means against each other, or at the same time, we use analysis of variance, right? Okay, so now, once we got past that, now we got into a situation. What about if I'm looking at male and female and whether they're diabetic or not diabetic? In other words, proportion of males diabetic, proportion of females diabetic, and so on and so forth. What would that be? That would be a situation where we have a nominal variable, right, which would be gender, and another nominal variable, which would be whether or not a person has a disease like uh, uh, like diabetes. And how would we deal with that? We'd set up a contingency table where male and female would be in the rows and diabetic or not. And what would we do there? We would do a chi-square test, right? And we'd also do odds ratio maybe, and we could do relative risk. So we had a couple extra things there, right? So we have scalar and numerical. We have the scale. We have nominal and scalar. We have nominal with more than two values and scalar. We have nominal and nominal. Well, what are we missing? We're missing a test for numerical and numerical. And that's exactly the test that we're looking at right now. This is how we find if there's an association between two numerical variables. And the name of that test is going to be correlation. Correlation, and we're also going to look at another kind of statistical function called regression. For today, we're mostly going to stick with correlation, and we're going to introduce regression. Next week, we're going to get into regression. And why are these important? Because a lot of the data we deal with is measurements, numerical measurements. And you can even, in some cases, take regression, this way we can analyze these two things, and you can actually involve categorical values in a regression. So you can look for an association between two numerical variables, but also include whether or not a categorical variable also influences that as well. In other words, what's the association between a person's age and their blood sugar? Well, what about, what's the association between a person's age and their blood sugar if we also consider their gender? How does that affect everything? So we can actually wind up some categorical variables in there as well. And we can even kind of move it around, and we can include many numerical variables. What can I use to predict a person's blood sugar? Well, maybe I can use their age. Maybe I can use their BMI. Maybe I can use their level of education. So maybe I can use all three of those things at the same time to predict what their blood sugar is. That's called regression also, except that's called multiple regression. Well, what about diabetic? If somebody's diabetic, okay, what's the probability that a person in the population is diabetic? Well, maybe I can predict what that probability is based on all these other factors, their gender, their how much sugary drinks, whether or not they drink sugary drinks, whether they do that. In other words, we can look at use this regression to look at a logical situation, like is it yes or no? Is a person diabetic or not diabetic? Yes or no? And see the probability that they're diabetic based on other factors, numerical and categorical and so on, right? That's called logistic regression. That's used in a lot of studies and statistical analysis nowadays. So it's an important topic for us. We're going to learn a bit about regression, and I'll even post an assignment for correlation, simple linear regression, maybe even a little question or two about multiple regression. Logistic regression, it's kind of an advanced topic. I'm going to introduce it and show you basically how it works, so you're aware of it if you see it being used, right? But we're not going to be asking you to do anything with it. Among other things, if you bought the base version of SPSS, it doesn't include logistic regression, like the $35 version doesn't include it. The $45 or $50 version, whatever it is, does include it. So I'm not going to be asking you to solve any problems with that. Okay, so let's go back to SPSS. Let's take a look at SPSS. So if I'm looking at this association between age and blood sugar, so far, what's the easiest way for me to just at a glance tell if there's an association between those two? What did we do that really demonstrated that very clearly? We made a graph. right? And what do we call that? The scatter plot, right? So that we plotted a point if age is the on the x-axis and blood sugar is on the y-axis. We plotted the point 30, 75 as a dot on those two axes. So I'm going to do that. I'm going to go up here to graphs. I'm going to go to legacy diet. There's a number, this chart builder function. There's a number of ways to build graphs. It's simplest way is just go to legacy dialogues. But if you want to get familiar with the other ways, you can certainly do that. So I'm going to click a simple scatter plot. And I'm going to tell it on the x-axis, I'm going to put age. On the y-axis, I'm going to put blood sugar. So now, I could have reversed those. As far as correlation is concerned, it doesn't matter which one you put in the x-axis, which one you put in the y-axis. You'll still get the same result for your Pearson's correlation coefficient, for that number that tells you how strong the correlation is or whether it's significant. Later on, when I get into regression, remember I said maybe I can predict a person's blood sugar from their age. Well, what am I implying there? I'm implying that age helps to determine the person's blood sugar. So in other words, age is an independent variable, and you can use it to predict blood sugar, which is a dependent variable. It depends on age. So x-axis and y-axis, right? So I'm going to start off by putting age in the x-axis anyway, since we may wind up looking at that, even though I don't have to at this stage. So I'm going to click OK and see what this table looks like. Okay, so here we go. There's the table. Does it look to you like there's an association between a person's age and their blood sugar? Sure, it does, right? Matter of fact, I can do a quick little trick. I can double click on this to get the editing window up for this graph, and I can tell it now where to go. Chart it. Here it is over here. I can tell it to fit a line to this data. And I'm going to say, okay, and it did it already for me. And what it did is it created a line that best fit all of these different values. Now, I'm going to give you kind of a abbreviated, kind of like simplified version of what's going on here. What's going on is it's not just looking at the difference. It's trying to place this line so that the distance to the values that are above it sum up to the same as the distances as the value below it. In other words, trying to even that out. And there is a single line that best fits that. In fact, it's really more a sum of the squares of the distances here, the differences between the line and what the individual values actually are, than it is the actual distances themselves. But SPSS creates that. We don't have to worry about doing that calculation. There's a recording of a lecture session that's on Blackboard for this session that goes into much more depth on how this calculation actually occurs, right? So it's a good idea, just listen to that, relax, have a cocktail, relax, sit back and just let that like wash over you. And you don't have to, functionally, we're going to work with SPSS. SPSS is going to do this calculation for us. We don't need to do the manual calculation that's involved in fitting this line to this. So there's an actual calculation involved. You don't have to do that. We'll let SPSS do it for it. But I'm sorry, there's something going on behind me again.
You know what that line is, the regression line?
That's yeah. Well, yes and no. We're gonna get to that. You're ahead of it. Right now, we're just talking correlation. Okay. Regression implies like there's some causation involved, and we're going to get to that in a little and predict ways that we want to use them to predict stuff. Right now, we just want to see if there's an association and see if how strong that association is, and see if it's a statistically significant association. In other words, maybe it's just due to chance. Okay, so let me ask you something. As age goes up, what happens to blood sugar? Goes up also. That's called a positive correlation. And what if blood sugar went down as age went up? That would be slope this way. That would be a negative correlation. So you're going to have positive correlations and you're going to have negative correlations. You're going to have strong positive correlations, strong negative correlations. Okay, so I'm going to take a look at this now. I'm going to analyze this. Oops, I need to close that. put it back. Okay. I'm going to analyze this. I'm going to analyze. We have a selection here under analyze correlate. This is bivariate correlation, two variables, right? Age and blood sugar. I'm going to click bivariate. Now notice that it doesn't care which one I put in here first. There's not two boxes like there was when we did the chart, because it doesn't care for correlation, which one is the cause and which one is the result, which one's the independent variable, which one's the dependent variable. Right now, it's only looking for an association. That's it. We're going to find Pearson's correlation coefficient. And again, this is a calculation. It's in the lecture in more detail. I'm going to click OK. Now, the table that we wind up getting gives us a number of results. The first result is it compares the age of a person to the age of a person. If I'm comparing a person to their own age, that's a perfect correlation. Right? It's going to be same number, right? So what does that correlation turn out to be? It turns out to be 1. So we know now, if we didn't know before, we know now that a Pearson's correlation coefficient of 1 means a perfect correlation. Every point is on the line. No points are off of that line. It's a perfect correlation, very predictable, right? In this case, we're looking for a correlation between age and the next column, blood sugar. And that correlation is 0.821. That's pretty close to 1, isn't it? 0.821. That suggests it's a good, strong correlation. Exactly. It's a strong correlation. Now, what do you think would be the number there if there was no correlation, no association between blood sugar and age? Basically, it would look like a cloud of points. What if there's no association? Bingo, 0. Exactly right. The correlation coefficient for no correlation at all would be 0, right? And what about if it were the same correlation, the same numbers, except that the age went up, the blood sugar went down? What do you think the correlation would be instead of 8.821? It'd be negative 0.821, right? A negative Pearson's correlation is telling you that it's a negative correlation. One goes up, the other one goes, as one goes up, the other one goes down. Okay, everybody comfortable with that? Okay, so if I were to show you, if I were to say, okay, here's two variables. This is A and this is B. I'm not even going to bother to tell you what they are. But if I had a plot, like if I had a scatter plot, something like this, right? And I gave you a choice here. I'm going to say that the correlation there is either 0.8 plus 0.8 or plus 0.4. What do you think it would be?
0.8.
Yeah, I think so too, right? How about this?
0.4. Or plus.
About 0, right?
Yeah.
Probably no correlation at all. It's just a cloud of numbers. In fact, if you were to draw a fit line, it would probably look something like this. Doesn't matter what age you are, you got the same blood sugar. It's the same thing, right? So what about if we had something like this? What do you think? How about negative 0.4,
Yes.
right? So you get the idea here, right? How well they correlate, how well the numbers match each other, determine how close it is to 1 or to 0. 1, 0, or negative 1, right? Negative side is negative correlation, like here, and the distance from the line, the best fit line, suggests that it's not such a strong correlation. Where if they had all been very close to this line, that would still be a negative correlation, but it might be negative 0.9 instead of negative 0.8. So we have two things that are helping us out here. Number one, R, the Pearson's correlation, R represents a situation, represents how strong the association is. Okay, but you could also get something that's just due to chance, right? That your particular sample looked like that, but not the population itself. So let me go back here to that window. Oops.
Lowercase r.
It's lowercase r, yes. It's here, I think.
Program.
Yep. Okay, and let's see. What was I going to bring up here? Something I wanted to show you here. I can't remember what it is now. Okay, so now we know it's a strong correlation because it came up to 0.821. How do we know that that's not due to chance? Well, we do have to do a statistical analysis to see what the probability would be that we would get this outcome if the null hypothesis was true. What do you think the null hypothesis is? Usually you start out with a point where you're saying, well, this is, there's no difference, or there's no association, or there's no something, and you're trying to reject that to say that there is an association. In this case, that there is a correlation. So what do you think the null hypothesis here is? There's no association, but we can put that in the terms of a number. What is it when there's no correlation? 0. We can say that the null hypothesis R is equal to 0. What's the alternative hypothesis? R is not, it could be either way, not equal to 0, right? R is not equal to 0. So if I told you that if I had this plot, remember this particular plot here, I'll draw it again. Okay, maybe this line looks like that or something like that. And maybe R comes out to 0.1. And significance comes out to 0.01. Okay, what does that tell you? What does it tell you about the association, about the correlation? Is it a strong association? Is it a strong correlation? 0.1 is not, it's a weak one, right? Look at all these dots, or, it's generally sloping upwards, but look how far away, look how scattered these are. It's not a strong association. However, but it's real, it's statistically significant. So it's not due to chance. There's a real association there. It just happens to be a weak association, right? So if you look at our result before, 0.821, that's a strong association. Is it statistically significant? It is. That's less than 0.05. So what does that tell you about our null and alternative hypothesis? R is equal to 0, R is not equal to 0. What can you say about that? We can reject the null hypothesis, R is equal to 0, and accept the alternative hypothesis that R is not equal to 0. Now, if this had been 0.1 and significance equals 0.01, we would reject the null hypothesis. If this had been 0.821 and the significant would have been 0.15, even though this appears to be a stronger association, we couldn't reject the null hypothesis because we didn't have enough data to give us a significance that was less than 0.05. So even though this seems to be a very strong association, if this is not less than 0.15, we can't say that that's not due to chance. 0.15. In other words, it's greater than 0.05. So I can't reject the null hypothesis. Instead of being 0.04, if it had been 0.15, right? Okay. That wouldn't be statistically significant. I couldn't reject the null hypothesis. Okay. So that's important to us. And it works the same way, negative or positive, it doesn't matter. Okay, so let's see what we can do with this now. Okay, so we have a basic idea of how this works. Oops, I've got to turn that off. Okay, so let's see what else I have here. Okay, 10 patients between 30 and 60 years old were randomly selected from patients in a long-term care facility. Following data, that's the one we just did. Don't need to do that again. See, I can go back to the other data I have there. This will go through step-by-step a regression analysis for you. You can open this up later on your own. You don't need me to show you this. Okay. If you go through that document, I just opened this document on correlation and regression exercise. If you go through that, it'll step you through what I'm doing right now. So if you forget about it, you can it'll give you what to expect when you work with SPSS. But I'm gonna do it like I'm gonna wing it myself without using that for now. So I'm going to pick a data set that I have here. I'm going to open it in Excel just to show you what it looks like. Okay, so here's a bunch of data.
Can you calculate this on Excel or no?
That's a yes, but with great difficulty. When you see the lecture, right, you'll see that it's a rather complicated calculation. So what do we have here? We have 52 subjects here, 51 subjects, because the top line is the titles or the variable names. What are the states? These are all states, right? California. What's telling us about California? It's telling us about the number of violent crimes, the murder rate. This is probably, when they say murder rate, it's probably per 10,000 or 100,000 or something like that. Poverty rate, that's probably a percentage. The high school graduation rate, the college attendance rate, the percentage of single parent households, the unemployment rate, and it's got a score there for metropolitan versus urban. How metropolitan is the area? What percentage of people live in a metropolitan area? So in New York State, that would probably be very high. It's 91.9, right? And in maybe not Mississippi, in Iowa, it's going to be lower. Well, it's 44.9, right? So that's what that represents. How many people, what percentage of people live in a metropolitan area? Urban versus rural. Okay, so this interesting. What's the nature of all this data? It's all, except for the names of the states, it's all numerical data. So if we're interested in seeing if the murder rate is associated with the rate of poverty, what kind of test could we use? Correlation. We could look for an association using correlation. If we're interested in knowing if the murder rate is associated with the percentage of single parent households, we could examine it that way. Or the unemployment rate is, or whether it's urban or rural, and that more urban or rural, and say these are all numerical variables. We can use correlation, and it's nasty little brother regression when we get to it to evaluate this stuff. Okay, so let's give this a try. So what do you think? What do you think is associated with the murder rate?
Are you limited to how many you can do when it comes to correlation as opposed to looking at all the factors?
That's a great question. Hang on to that question for just a second. The answer, no, you're not limited. You know, because we're going to do something called when we get to the regression, you'll see that for as far as correlation is concerned, correlation is just two variables. You only do it with two variables. Regression, now you can get into using multiple variables, but we haven't got there yet. That's why I'm so what do you think I can compare? What do you think is associated with murder rate the most? Poverty, high school, college, single parent household. Poverty. Okay, let's give that a try. So we'll go up there to this is open in Excel. Let me close that off and open in SPSS. Is it open in SPSS? Do I have it? I don't have it open in SPSS. Did I download it yet? Open data. I don't know if I downloaded it yet. No, I didn't download it yet. Let me go back and download the SAV file. Okay, and I go back to SPSS. Nope. Yeah, that was SPSS. Open data. And here's violent crime.sav. Open that. I can see it because it's .sav file. If we're an Excel file, I wouldn't be able to see it unless I told it to look for other kinds of files, Excel files and so on. So I am looking for a correlation, an association, analyze, correlate, bivariate, two variables. I'm looking for an association between the murder rate and the poverty rate. Okay, Pearson's correlation coefficient. I'm going to say, okay. Before I do that, what is my null hypothesis?
There is no association.
No correlation between these two things, but really I'm phrasing it. I have a statistic I can use now, right? R is equal to 0. Null hypothesis. Alternative hypothesis, R is not equal to 0. So I'm going to click OK. Let's see what we get. Okay, so murder rate, Pearson's correlation coefficient, the murder rate, when I compare it to the poverty rate, is 0.426. Okay. It's associated. It's not that strongly associated, but it's definitely associated. Can I reject the null hypothesis and say that there is indeed an association, a correlation between these two?
You can't.
Significance is 0.002.
It's less than 0.05. So yes, you can reject the null hypothesis, right?
Yeah,
Right.
you can't.
In other words, this is for us to get this extreme a value, given the data that we have, that would only occur 0.002, that percentage at a time, if the null hypothesis were true. So since there's less than a 5% chance the null hypothesis is true, we can reject it, right? We're willing to take that risk and reject it. Okay, so that's pretty interesting, right? So I want to plot this. Let me analyze, graphs, legacy dialogues, and scatter dot. So I want to get a look at this. And usually it's a good idea to do this anyway. And again, it doesn't really matter which one. I'm going to put the poverty rate in the x-axis and the murder rate in the y-axis, because we was thinking poverty might cause the murder rate to go up. Okay, let's see what this looks like. Oh, look at the data. Whoa, wow. That's pretty weird considering that, we had that nice correlation, right? Well, what do we have here? Look at this guy up here. We have an outlier. Anybody want to guess on what that outlier is? Think about this. There were 51 states listed. So what do you think that 51st thing that they listed as a state was?
DC.
Bingo. Exactly. It's Washington, D.C. And apparently this was during a period when they had a very high murder rate and it's a relatively small population. So even a few extra murders is going to impact the rate, right? Because it's a relatively small population. So let's go back to the data, this data file. Okay. And this is Columbia, and look at this. Wow, the murder rate is 41.8. Look at all the others are in single digits. You know what I'm going to do? There's a couple of ways to do this in SPSS. There's a way to filter out certain data so it stays in the data set, but you're not including it. But I can also just go up here and say clear and remove that. So I'm saying to myself, something weird's happening there. So it's not even really a state. They don't have they don't have representatives. It's more of a town. I mean, if you've been to DC, DC is pretty small, right? So I don't think it's really representative of whole state. So I'm going to remove it and not consider it I'm going to make that judgment that I'm going to remove it as an outlier. So let's take a look at what our graph looks like now.
It's a murder rate. It's not a murder count.
Right, it's a rate, which is good because then it adjusts for the population. But even then, it's a smaller population than the states, so it may be skewing us quite a bit. So I'm going to go here, and I'm going to still already set up. I'm just going to do it again. See what it looks like this time. Well, look at the difference now. Look at the way this chart looks now, right? So it's a lot easier now to see this correlation, right? So I mean, you're going to wind up with issues like this when you are working with numerical data, and there may be outliers and so on and so forth. One of the things you might notice is we're trying to fit this line so everything is balanced above and below this line, right? Balanced in a sense. You'll get a better picture of that when you play the lecture, right? So it's balanced. But let me ask you something. You ever been on a teeter-totter? Or what do they call them? What do they call them? Teeter-totters, right? It's just seesaw, right? Seesaw or teeter-totter, right? What happens if you go to the very end and push down? Has more of an influence than pushing down on the middle, right? Or something like that, right? So when you have a value that's very high at either end of this line, it has more of an influence than the other values. So you got to be a little concerned when you see something a little weird like that at the end, instead of out here, all the way out there. So a couple of things. You want to be concerned about the values that are either extreme, number one. And number two, you only consider correlations and regressions for the areas that you have data for. So like in other words, even though this line seems to continue up here, right, doesn't mean that your correlation applies to a poverty rate of 25%, right? You want to stick to the area where you have data. In other words, from 7.5% up to about 18% poverty rate, right? You don't want to speculate about areas of this graph where you have no data. Okay, so this is pretty interesting. But you know, let's say one of the states was missing. And you know, we didn't, you know, they didn't do the data. We don't know the murder rate in that state. And you know, we're stuck. We really need to have a rough idea what we need to find some way to predict what the murder rate in that state, so we can, you know, figure out how to allot money for crime prevention or poverty, anti-poverty programs or something like that. So I need to be able, since we didn't do that state, I need to be able to guess at it. But now, since I know there's an association between the poverty rate and the murder rate, maybe I can use the poverty rate to predict what the murder rate is. That would be great, right? Because then you could use that kind of logic for a lot of things where you can get one set of numbers that are very good at predicting something else, which is difficult to measure. Okay, so let's say that I wanted to do that. Well, you know, basically this is telling me that the way that poverty is related to murder rate is the way that this line is sloped, the way that this line is drawn. Well, what does that mean? Okay, now we're going to go back to algebra. Remember algebra? Okay. Not Algernon, algebra. You know, you guys should know it's Algernon. Algernon was that. That was Flowers for Algernon. It was a novel in the 60s or 70s. Anybody ever read that? Flowers for Algernon.
No.
I think they made a movie out of it. Made a couple of movies out of it. It was about a mouse. Somebody was experimenting with drugs to increase intelligence in mice or something like that. And somehow or other, they gave it to a person. Person was like the janitor. It was a very simple-minded janitor. I think it's called Charlie or something like that, the movies, right? And Cliff Robertson, I think. Cliff Robertson? Right?
I think I read the book in school.
Yeah. Flowers for Algernon, right? So they gave it to and he suddenly became super intelligent after he took this brain boost, but it got a very sad ending. So I won't tell you if you ever read it.
Yeah, I kind of remember.
Yeah. So why did I bring that up?
Yeah, I don't remember, I didn't
Yeah.
remember it vaguely.
I need a little bit of that.
I wish I could remember why I brought that up now, after I strained my brain trying to come up with that. But so at any rate, so let's say that line now, we can use that as a predictor. So we're going to, oh, you know what, as I was talking algebra, and the name Algernon came into my head for some reason. That's what it was. Okay, so let's take that line that we were just looking at, right? Okay, so here's the line we're just looking at. It's a straight line. Remember what the formula for a straight line was? Y is equal to mx plus b. Yeah, you look at that look of recognition on your faces, right? Okay. I'm going to start with the simple one. I'm going to extend this line a little bit. I'm going to make it dotted. I'm going to extend that line, and I'm going to extend the line that way, because I want to put together a formula that represents this line. So y is equal to mx plus b. Well, when x is 0, this is the point where x is equal to 0, where it crosses the y-axis, right? So we call that point the y-intercept. X is equal to 0. So if x is equal to 0, what is y equal to? M times 0 is 0, so y is equal to b. That's why they call it the y-intercept, right? Okay, so what does the m stand for? The m is the slope of the line. And the slope of the line is the change in y over the change in x, right? So if we have a line, if the m is equal to 1, it means for every time you increase the x-axis by 1, you increase the y-axis by 1. If the slope is equal to 2, every time you increase the x-axis by 1, you increase the y-axis by 2. So a slope of this might be a slope of, I don't know, of 0.75 or something like that, because it's not 45 degree, right? But that's what the slope represents, right? This m represents the slope of this line. In statistics, for whatever reason, I have no idea, they kind of wing this a little bit. They call this y is equal to beta 0 plus beta 1 x, where this is the slope and this is the y-intercept. Doesn't matter what letters you give it. A straight line, formula for straight line is formula for straight line. Just give, you can give it whatever numbers you want to give it to, right? So if we knew what the slope of this line is and what the place where it crosses the y-axis, that defines one specific line. That's everything we need to know to draw that line, right? So, but now the axes that we're using, the x here, the x in this case is the poverty rate, and the y in this case is the murder rate, right? So in this case, I could say the murder rate is equal to the y-intercept, right, whatever that happens to be, plus the slope times the poverty level. So if I know what the y-intercept is, and I know what the slope is, I'm writing with I'm scratching on the pad here. Is it down too low? Is it down too low? Is it down too low? You can't see it? Is that it?
Yeah, I couldn't make out that last.
Yeah, let me try it again. I'll try it again. Try it a little bit. The murder rate, you know, I've been having so many problems with using the trackpad in this room because I keep losing. I don't know if it's interference in here. The trackpad has problems, or I get knocked out on Wi-Fi when I have it connected and I'm using. But I use it all over the place here, except for this room. The murder rate is equal to the y-intercept, beta 0, plus the slope, right, times x. In this case, x is the poverty rate, right? So if I know the y-intercept and the slope for this line, I have a formula that if I know the poverty rate, I can use that formula to predict the murder rate. That's regression. That's what we call regression. When we develop a formula that's predictive, that associates the association between the independent variable, the poverty rate, and the dependent variable, the variable that depends on it, right? So that we can predict it with this formula. We're looking at the simplest form of this. It's called simple linear regression because the relationship is a straight line, right? There's a lot of relationships, not straight lines or other shapes, right? They could be parabolic or asymptotic or something like that. But in this case, we're dealing with a pretty simple relationship. Okay, so if we could just figure that out, that would mean that we have a way to predict what the murder rate is based on the poverty rate. So in other words, that can do two things for us. Now imagine what that can do for us. One thing that can do for us is if we're missing data here, if we have a state where they didn't give us the murder rate, we could use the poverty rate to estimate what we think the murder rate might be in that state. The other thing that we can do here is remember the slope. Remember that slope? It's the change in the y value over the change in the x value. It's a relationship of the two changes. That can also tell us that, gee, if we can reduce the poverty rate by 1%, what kind of effect would that have on the murder rate? So that slope could tell us that if we reduce the poverty rate by 5%, the murder rate may come down 3% or 10% or 20%, right? So we can see in advance what the likely outcome of our efforts from a public health intervention standpoint might be. Can you see how valuable this is? That could conceivably be in like deciding how to spend public health dollars and understanding what the relationship between these variables are. Let's try another one. Let's try analyze descriptive statistics, correlate bivariate. And I'm going to try, instead of murder rate, I'm going to try single parent household. And click OK. Okay, now this data is very old, but it's real data.
It's still murder rate?
Still murder rate and single parent house. Oh, no, it's just the poverty again. I don't know, it didn't change it. Hang on a sec. Descriptive, correlate. You know, I probably didn't move the other one at single parent. Poverty rate, single parent. Oh, yeah, I didn't. I murdered. You're right. Okay. Okay, let's see what the Pearson's correlation coefficient is. Well, look at this.
0, 0.
There's a higher level of correlation. It's even more significant.
Yeah.
Single parent household. So
This is better.
maybe public health dollars might be better in trying to keep families from splitting up rather than attacking the poverty rate directly. Maybe that's a better way to stop jailing them. There you go. That's one of the reasons why in poor neighborhoods, and one of the reasons why they're split up is because one of the family is in jail. Yeah, absolutely. Right. So, and that, believe me, that's one of the reasons why we're seeing so much activity on trying to reduce the incarceration for minor crimes, minor, especially victimless crimes like marijuana and stuff like that, drugs. So yeah, look at that. I mean, if this, this data is real, it's very old, right? It's not anywhere like, it could be 20, 30 years old or something like that. But I mean, this is the kind of thing that we can examine and we can start to understand better what the influences might be of what kind of interventions that we might do. So let's take this the next step. I'm going to say to analyze, I'm going to go to regression.
Can you explain the significance of 0, 0?
It's less than 1/10 of 1%. In other words, it only gives you 3 digits. So if it were 5%, it would have been 0.05, right? The probability you would get this this extreme alignment of these things, not really just this, it's really the number of values you have and how close they are to the correlation, the regression line, right? But it's a combination of factors. So 5% means that there is 5% chance that even what we see here is that the null hypothesis is true, that it's not a real association, right? 1% would say it's 1% chance that there's no association. The null hypothesis is true. 0.1. I'll get to that in a second. That's it's the same thing. I'll tell you why in a second. Okay, so the 0.00 means it's very low. Doesn't mean it's really zero. It's just that means that 0.0001 would be 0.1% chance, right? 0.0001 would be 1/100% chance, but it doesn't display more than 3 digits. So it could be 0.001. It's highly significant, right? Way less than 5%. So no problem rejecting the hypothesis. So what SPSS does, and you saw it do this analysis of variance also. It does it compares single parent household, presents single parent household to single parent households. Why did it do that? I don't know. Then it compares single parent households to the murder rate, which is what we're after. But then it goes and then compares murder rate to single parent household. Well, you just did that, right? So what did you get? You get the same result. They're both points. It's the same thing. Yeah, it's just it does every permutation automatically, even though we know that it's going to be the same number, right? A murder rate to murder rate is 1, point and same significance and so on. So it didn't change anything. This is a sample size, right? It didn't change anything. It's just that it does it every which way. And in the analysis of variance, you saw that it would compare the mean for group A to group B, group A to group C, group A to group D, and then it would compare group B to group C, B group D, and so on and so forth. And then it would go back and it would compare group D to group A and B. And you know what I'm saying? It would do it twice, everything twice, right? Or everything, it would repeat every possible combination twice. I don't understand why it does it. It's a remnant. Yeah.
So significance is the tails of the.
Yes. So in other words,
it's out of the tails.
It's further out than 2.5% on both sides.
Right.
So in other words, that distribution is the likelihood of all the outcomes that you might have if the null hypothesis is true. So you want it away from there. You want it outside of those tails, so that you know that the probability that the null hypothesis, that this is a result that you would get when the null hypothesis is true, is very unlikely, right? So if that were 0.04, that would indicate there's a 4% chance that the null hypothesis is true, but you're rejecting it anyway. Why are you rejecting it? Because if you didn't reject it, you would never reject it. In other words, if you had to be absolutely sure then you're not doing statistics anymore. You're doing something else, right? You're sampling everybody. You're doing a census. Then you're not doing a statistical analysis anymore. So that's the likelihood that outcome would be true with the null hypothesis.
Hello?
True. So since we have to set a reasonable standard, in other words, if we were to do a study and in order to get that under 0.01, in order to get that under 0.05, we determined that, when we're trying to calculate our sample size, we determined that, gee, if I do a sample size of 100, I got a pretty good shot at getting that significance under 0.05, so I can reject the null hypothesis. But if I wanted to get it under 0.01, I would have to have a sample size of 1,000, right? So you make a reasonable judgment that, gee, in order to conserve resources, I'm going to say that 4%, less than 5% chance of being wrong is okay with me. Now, are you wrong? Yeah, it happens all the time. You read about it in the papers. Oh, this study said that, corn makes you grow hair on your toes, right? And then somebody else tries to replicate that study. And look, here it is. It's like, it's statistically significant, right? It's like the significance is two-tailed significant is 4%, So yeah, it's statistically significant. But then 4% of the time that could happen, even if it weren't true, right? So how many studies do you think they do how many studies, the colleges, the corporations, the National Institute of Science, how many studies do they do a year? The thousands, tens of thousands, right? So how many of those statistically are crap? They're wrong, right? But
How do you know
you don't.
what to set your outcome? You just said.
Oh, yeah, it's a matter of resources. Depends on how important it is, and it depends on the resources you have, right? So in other words, if we're testing a drug that has really severe side effects, and we really want to know if this stuff works, right? And you say to yourself, oh, it looks like the stuff works, but the significance is only like 7%, 8%, it's 5.2, right? So, gee, I don't know. It's going to kill the people we give it to if it don't work, right? So that you might want to have, set alpha at 1%. On the other hand, if you're doing a food study and you're saying to yourself, well, we're studying the preferences, customer preferences for oatmeal, whether they like maple or they like brown sugar in their oatmeal or something like that. Well, I mean, if you get that wrong, nobody's going to die, right? So maybe 5%, certainty is, like 95% certain is good enough, right? 1% chance of being wrong, kind of like being 99% certain, in a sense. You don't tell a real statistician they ever said stuff like this, right? But I mean, because they look at this from the perspective of these being possible outcomes if the null hypothesis is true, right? That's really the way a statistician would look at this. If you cheat a little bit and you say to yourself, well, that 0.04 means I got a 4% chance of being wrong if I reject the null hypothesis, a statistician would frown at that a little bit. If you said that a 4% chance of getting this extreme an outcome, if the null hypothesis is true, that's the way he would probably phrase that, right? But I think it's okay if in your head you say to yourself, gee, it's 4% chance of being wrong, because it kind of is really, that's kind of not like a ridiculous way of looking at it, so in this case, there's a very, very tiny chance of being wrong if you reject the null hypothesis. Yes?
So seeing how the murder rate is 0.67, so you would still reject that.
No, you would reject it. The 0.677 is the Pearson's correlation coefficient. Remember, 0 means no correlation. 1 means a good, strong, a perfect positive correlation. -1 means perfect negative correlation, right? That gives you the strength of that correlation, how close those points are to the line. The significance tells you whether it's due to chance or statistically significance, right? So we want that number could even be 0.07, right? And still be statistically significant. That's telling you, what is that telling you? That's telling you a very weak association, but it's a real association. Even though it's weak, one doesn't really determine the other that well. It's a real association. It's not due to chance, or not likely to be due to chance. Okay, so that's another way we might look at this. So now let's go to regression. Analyze. regression. Now notice on my version it says binary logistic. If you have the cheaper version of SPSS, it's not going to have that, but it will have linear regression. Regression, linear means we're assuming that the relationship is a straight line. Big assumption, but we're making that. So now notice I got two boxes here, not one, right? Because it makes a difference now which one I put into which box. With regression, we're saying that the relationship is causative. One of these causes the other. Something causes, it's either the murder rate causes the single parent household rate to go up, which I guess is true if like 90%, if they're getting like a ridiculous murder rate, 80% of people are dying, and that's why so many single parent households, because they're all dead, but that's probably not the case. That doesn't make any sense, right? So it makes more sense that the way that this works is that the percentage of single parent households it might have an association where it's causing a higher murder rate. So the independent variable is the percentage of single parent household. The dependent variable, the thing that depends on the independent variable, is the murder rate. So I'm going to put them in there. So it's typically the independent variable is the x-axis, and the dependent variable is the y-axis, right? So I'm going to put the single parent household rate into the independent variable. I'm going to put the murder rate into the dependent variable, and then I'm just going to click OK. That's enough for us right now. Okay, so now basically we've just repeated our correlation calculation. And if you look now, there it is, 0.677. Our Pearson's R, our correlation coefficient, some reason it uses a capital R, I don't know why, but where most texts would probably use a lowercase r to emulate rho for the population. Okay, but don't worry about that, it's R. 0.677 is the correlation coefficient. That tells us how strong a correlation it is. Closer to 1, the better. It's a positive correlation. As the rate of single parent household goes up, the murder rate goes up. So this suggests a positive, and it's a pretty good correlation. 0.67, it's getting closer to 1. Now notice that there's a value here called R squared. Literally, if you were to calculate this, it'd be 0.77 times itself. It's 0.459. Now that's going to be significant to us in a second. That's an important number for us. And again, in the lecture, go into a bit more detail I'm going to go into here, but I'll tell you functionally how you might use that. Let's leave that aside for right now. So the next thing I'm going to look at is the significance. This gives you a more detailed view of how the significance is calculated. It's basically a form of ANOVA, and the significance is 0.000. So we know that correlation is statistically significant. It's not it's not due to chance. So now I'm going to come down here to this last chart, coefficients. Now remember, what is this all? What is our why are we doing all this? We're doing all this because we want to have values for our formula. Y is equal to mx plus b, or whatever version of formula that you use. Okay, so we want to fill those in. So our murder rate, hey, good night. Our murder rate is equal to the slope of x. What's x? X is the poverty rate plus the y-intercept. So what I need SPSS to tell me is what is the murder, what is m, what's the slope of this line, and what is b, the y-intercept. And that's what these numbers do. The constant, this number that's identified as a constant, that is the y-intercept. And this number that's identified as next to single parent is the slope of the line. Okay, it's a positive number. Why is it a positive number? As the rate of single parent households go up, the murder rate goes up as well. So our formula is the murder rate is equal to the slope, which is 0.56, times the poverty level plus the Y-intercept, which is a minus, actually turns into be a minus 8 point, I'm going to call it 8.2. I'll round it down to 8.2. Okay, so if I were to tell you, there's a state where they didn't give us the murder rate. We don't know what the murder rate is, but the single parent household, not poverty rate, that's single parent household. That's SP, single parent. Okay, I'm confusing myself here. Okay, so the single parent household rate is 10%. What do we think the murder rate is? We think the murder rate is going to be 0.56 times 10, which is 5.6. That doesn't make any sense, minus 8.2. Do I have data in that range? I think 10, that might be low. I think the reason why that's happening is because we don't actually have data in that range. Say 20%. Say the single parent household is 20%. 20% times 0.56 would be 11.2.
What's the Y-intercept again?
The Y-intercept is the place where it crosses, B. That's B. It's negative 8.24. Okay, so 5.6. If the single parent household rate is 20%, this would be 11.2 minus 8.2. In that state, we would expect the murder rate to be 3%. But whatever that number was, 3. Whatever that rate was, 3 per 1,000, 3 per 10,000, or something like that. Let me just take a quick look at the graph for this. Okay, graphs, legacy dialog. Oops. Okay. Oh, I know why it's doing this. Okay. Oh, I screwed this up again. I picked out poverty instead of the single parent household. That's why the numbers are coming out. So single parent household goes at the x-axis. I'll do this again. Here's the correlation, but it's a pretty strong correlation. That's why it's 0.67, a nice strong correlation. But we don't have data below 10%, below 10% family. The lowest state is still above 13% of families are single parent households, right? So remember, we want to stay within that data range. So let me go back here and say analyze, regression, linear, and single parent. Oh, I did do it. Okay. Okay, and we get the same thing. Okay, so the murder rate, say the murder rate is, let's say the single parent rate is more likely something like, if this is from 13 up to 30, I'm going to pick a number like 20%. So the murder rate we're predicting for a state that has a single parent a family rate of 20%, the murder rate, we expect it to be equal to 0.56 times the single parent rate, which is 20%, 20, minus, plus, in this case it's minus 8.2, right? So 56 times 20, 0.56 times 20 is 40,
What was the B?
10. What's that?
What is the B?
The B is the Y-intercept,
Oh,
right? Right. This is the B.
Oh, okay.
This is MX plus B. Okay. Okay. So 20 times 0.56 is 10. Plus 12 is 11. Is 11.2. 11.2 minus 8.2, yes, is equal to 3. So the murder rate is equal to 3. That's what we predict based on this information. So now I'm going to go back to the raw data. I'm going to clear all these. Okay. I'm going to go back to the raw data and take a look at this. And let's see, if I had a single parent rate of 20%, here is closest I can find right off the bat is 19% single parent household rate. And what is the murder rate for that state? 2.9. We got pretty close at predicting that, right? So what good does that do us? That helps us predict things like this. It also helps us by saying, well, gee, if it's 25%, like at 25%, it would have been some other higher number. If we can reduce the rate of single parent households,
I'm sorry, how you selected 2.9 on here based on?
single parent house, I picked this Hawaii. In Hawaii, the single parent rate is 19%. I just picked it out because it's close to 20. I wanted to see how well our formula agreed with this particular line, and at 19%, the murder rate was 2.9. Okay, which is pretty close. But you want to know something? It's not always that good, because you saw not all little things wound up on that line. So one of the things we might be interested in is how far off our predictions are. So, like for instance, how well did we match the murder rate and the single parent household rate for Alabama or for Alaska? Okay. Well, I'm going to count SPSS, calculate that for me. I'm going to say analyze. I'm going to say regression, linear. I'm going to go back and the same thing. I'm going to click on this button that says save. And in here, I'm going to click off unstandardized predicted values. In other words, it's going to use that formula and it's going to calculate for each state based on what the single parent household rate is. It's going to calculate what the formula would tell you that the murder rate is. So I'm going to go ahead and do that. Okay, and let's see what happens. Well, not much changed here. However, if you go to the data page, the data, we now have another column here, the predicted value. So like in other words, for Alaska, right? Alaska, based on the single parent rate of 20 household rate 23.2, it predicted using the formula that the actual murder rate would be 4.7. And what is it in real life for Alaska? It's 4.3. Okay, what about for Arizona? For Arizona, it predicted 4.9. Oh, it was pretty far off in Arizona, right? The difference between what the line predicts and what the actual rate is for that community is called the residual. So you have the predicted values and the residuals. Well, it's going to be a pain in the butt for me to calculate every residual. I can get SPSS to do it for me. Regression, linear. I'm going to go in here and save. And now I'm going to ask it to calculate the unstandardized residuals. Don't worry about standardized yet. We'll talk about that next week. So I click OK. And now it's going to add another column. Okay, it gives me the predicted values and it gives me the residuals. Like the first one, Alaska was off by very little. The next one was off quite a bit. And these are all the differences between the predicted values and what they actually were. Okay, well, why are we even interested in these residual values? Because the reason why we're interested in it is because remember when we were looking at that line? What's that? Yeah, because why is it? What does that residual tell? Those residual values tell us. Well, the residual values, if our correlation, our regression, is true and it's a good predictor and it's predicting things correctly, right? Those residual values should just be due to chance. That, this time we're a little lower, this time we're a little higher, and so on and so forth, right? That's what those residual values should look like, that they're due to chance. Let me draw the fit line here. Okay, so hang on, I'm gonna get to that in a second. Okay, and look at them over here. Look at this. Well, that's pretty interesting. So if they're not due to chance, let's say we have a situation, we look at this, and there's a lot down at this end of the line, there's a lot more that are below the line, and at the other end, there's a lot more above the line. it looks like what we really should see is that they're pretty evenly distributed across the bottom and the top of the line, with more of them close and fewer of them farther away. That looks about right there, right? We want the distribution of these residuals, the differences, to be random and normally distributed. In other words, most of them a little bit different, but fewer and fewer and fewer and fewer of them very different, either on the low side and on the high side, right? So if we see a pattern here where they're not normally distributed, we got to be worried that there's some other factor in here that's influencing this whole thing. That we got to be worried about, is like really kind of messing up our understanding what's happening. Now I want to show you one more thing, and that one more thing is that little r squared that we looked at before. That little r squared is important to us, because what that r squared tells us is that 46%, I can round it off to 46% of the variability in the dependent variable, the murder rate, is predicted by the independent variable, the percentage of single parent households. This is basically telling us that half of the variability that we see in the murder rate can be accounted for by the rate of single parent households. That's a lot.
Yeah.
That's pretty damn significant, right? So that's important to us. And had that been only 10%, we'd be saying to ourselves, well, it's nice that that helps predict it, but gee, there must be something else that predicts it better than this.
What's that called again? The R squared?
R squared, yeah.
What's the name of it?
It's just R squared.
Oh.
Yeah, that's it. There may be another name. Maybe I'm not thinking of it. Maybe another name.
Isn't R-squared a big thing, big deal?
Yeah, it's a big deal because it helps us understand how much of the variability of the dependent variable is determined by the independent variable. And if that's low, it doesn't help us that much. Now, you had mentioned, gee, what if I add another variable here? And this is, we're going to end with just this thing. I think it'll be a great time to end. And let's say, I need to be on the data. I have two files open at the same time, so I need to make sure I'm on the right file. Okay, that one. Okay, I'm going to go back here and analyze regression. Whoops, I mean to do that. Analyze regression.
Can we do unemployment?
Linear. What's that?
Unemployment?
Unemployment. Yeah, okay, let's try unemployment. Except this time, let me move unemployment in here with single parent household. Okay. As a second variable, a second independent variable. And I'm going to click OK, just to take a quick peek at this. Now, if I consider both of them at the same time, doesn't seem to help very much, does it? Right? You know why? Because there may be a certain amount of codependence. In other words, single parent household may be associated with households that have a lot of. So let's go back and try one that maybe don't have this kind of codependence. Let's see. Okay, regression, linear. Let's get rid of that. And how about high school? How about
What about violent crime?
violent crime? Yeah, but that's the same thing as murder rate. Yeah, kind of same thing as murder. Okay. Okay. How about if we combine single parent household with rate of high school graduation? Okay. Oh, well, look at that. Now, when we did this, this is a better predictor, this formula. And now what does this formula look like? This formula now has two variables in it that are independent variables. This formula now looks like the murder rate, murder rate is equal to the single parent household, right? Right, and this, excuse me, the slope, which is the, let's see, where is it? I got to scroll up further. Okay, so now we have two slopes here. We've got single parent and we have high school. We have two coefficients. So now single parent, right? Single parent, that's 0.4, right? I'm rounding it off on purpose because we don't have much time, times the single parent rate plus So we also have in here high school plus negative 0.197 times the high school graduation rate plus the slope. I'm sorry, it's so sloppy. But imagine what I'm trying. Let me do this. I'll try it again. Murder rate is equal to 0.4, right from down here. You see where I got the 0.4, right next to single parent.
Yes.
0.4 times the rate of single parent households. Single parent. Okay. Minus, I'm going to call it 0.2. Make it easier. 0.2 times the high school graduation rate plus B. B in this case is 12 plus 12, right? Okay, so let's see what this tells us about the murder rate. The murder rate goes up when the single parent household rate goes up. What does it do when the high school graduation rate goes up?
Down.
It goes down. It gets a bigger negative number. So we can see that this is taking into account the single parent rate, household rate, and the high school graduation rate, which is bringing it down. So they kind of balance each other out. And overall, this gives us a better predictor. In other words, now, if we combine those two variables in our regression and call it a multiple regression, those give us a better predictor of what the murder rate is. In other words, now we can say that 52% of the variability in the murder rate is due to these combined factors.
Is there a thing, explain variance?
Variability. In other words, the change in one, the way the change in one affects the change in the other.
Does that affect modification?
Not quite the same thing as variability, but yeah, but you got the right idea. Yes.
Does that affect modifier? That's an effect modifier.
I guess in a sense. So I think this is pretty heavy stuff. It's very different than the other stuff, right? Very different than chi-square and so on and so forth. When you look at the lecture, you'll see that it's a little bit, the calculations, it's not like the kind of thing that I could just chi-square, I could just show you boxes and show you a few tables and this nice easy math and stuff like that. That's why it's been more complicated, the math and the theory behind this, but it's really valuable because it helps us really quantify these causes and these effects. In other words, now we understand when we do something, when we do an intervention, what we're looking for is an outcome and whether or not it's likely to give us the results we want, right? Or what we have to do to get the results we want. All right, so I think it's a good time to call it a night. Okay, how you guys doing online? Oh, so I got an 11.2. Thanks for the help on the math. I appreciate it. Okay, take care, guys, online. Good night. And next week, we'll work on this now. I will post, again, I'll post some more information about the project if you want to do the project. I will post an exam covering this material and next week's material by the 15th, and you will have until the 20th, which is Friday night, to get it done. And if you choose to do the project will be due the same time. But I can't mess around. I got to get grades in, right?
Yeah.
So that's literally the 20th is like the last day of the finals week. Actually, I think the 19th technically is the last day of finals week. So really, I'm giving you an extra day. But I can't be waiting for you next week into into Tuesday one, because I got to get the grades in pretty quickly. Okay, so we're on the home stretch here. Good night, guys.
Thanks, Dave.